Hi folks! The following video is our first one on radicals. I will be talking about the structure and stability of radicals, new patterns for radical reaction mechanisms, and a particular reaction known as methane chlorination. Radicals refer to molecules that contain an unpaired electron. And in order to think about how radical molecules form, we need to consider two different ways in which bonds can break. Bonds can break by either heterolytic or homolytic bond cleavage events. In a heterolytic bond cleavage, a bond between two atoms, labeled here X and Y, breaks, and both of the electrons go to one of the elements of the bond. In this particular case, the electrons are going to atom Y, so I would draw this as a curved arrow from the middle of the XY bond to Y. This would form an X cation and a Y anion. So notice ions have formed in this heterolytic cleavage. Most organic reactions involve heterolytic cleavages. For example, consider a loss of leaving group to generate a carbocation. That would be an example of a heterolytic cleavage event. And in a reaction mechanism, you would use a full-headed arrow to show the movement of two electrons. So by full-headed, I mean there's a complete V at the end of the arrow. The arrow shows where the electrons are coming from with the arrow tail, and where they're going to where the arrowhead is pointed. If instead a homolytic bond cleavage occurred between two atoms, radicals would form. So notice there were originally two electrons in the bond between atoms X and Y, and those electrons are distributed evenly between X and Y in the radical products. We are going to use a new type of arrow for this radical formation, and the homolytic cleavage is going to involve two curved arrows. One arrow pointing toward X, and one pointing toward Y from the middle of the original XY bond. Homolytic bond cleavages are going to occur in radical reactions, which we'll be exploring in this chapter. And we use a new type of curved arrow known as a fishhook arrow for these reactions. The fishhook arrow, in which only half an arrowhead is present, depicts the movement of a single electron. So for the fishhook arrow, it still depicts where the electron is going from and going to, but instead of a two-electron movement, you're showing a single electron's movement, with each fishhook arrow drawn. Now let's consider the structure of radicals compared to other carbon species we've seen previously. We've seen many examples of carbocations featuring a carbon with 3 bonds and a positive charge. The carbocation is sp2 hybridized and trigonal planar with an empty p orbital. We've also encountered carbanions, which are carbons with 3 bonds, but now they have a lone pair and a negative charge. Carbanions are typically sp3 hybridized, as long as they aren't engaged in resonance, and this makes the carbanion trigonal pyramidal. Radicals, which contain a single electron, are between these two extremes. The structure and geometry of radicals is a bit complicated, but we're going to approximate their geometry as being trigonal planar, meaning that we'll approximate the radical as being sp2 hybridized with a single electron in a p orbital that is above and below the plane of the radical molecule. The geometry of this radical is going to become important in future videos where we're going to talk about stereochemical outcomes for radical reactions. In terms of considering the relative stability of different radicals, we're going to see the same trend for radical stability that we saw for carbocation stability. This is due to the fact that radicals have incomplete octets and 7 valence electrons instead of 8, so they are also stabilized by hyperconjugation. the donation of electron density from neighboring carbon-hydrogen bonds into the partially filled p orbital of the radical. So our stability trend for radicals mirrors that for carbocations, in that a methyl radical is the least stable, followed by primary radicals, secondary radicals, and tertiary radicals, where the primary, secondary, and tertiary refers to carbon substituents coming off of the radical containing carbon. The stability of these radicals is consistent with bond dissociation energy values for carbon-hydrogen bonds, where the carbon is either a methyl, primary, secondary, or tertiary. So recall that bond dissociation energy gives us information about how strong a bond is. The bond dissociation energy for this carbon-hydrogen bond in methane is 435 kilojoules per mole. And notice that the carbon-hydrogen bond strength drops, going from a primary carbon-hydrogen bond to a secondary one to a tertiary one. The trend that's observed is that breaking a weaker carbon-hydrogen bond forms a more stable radical. So notice this tertiary carbon-hydrogen bond is the weakest one, and it leads to the most stable tertiary radical. Similar to carbocations, radicals can also be stabilized by resonance, and in fact, resonance-stabilized radicals are even more stable than tertiary radicals. Two common resonance-stabilized radicals are an allylic radical, where a radical is adjacent to an alkene, or the benzylic radical, where a radical is adjacent to an aromatic ring. For the allylic radical, the unpaired electron is either on the carbon on the right or the carbon on the left in the resonance contributors. And to draw this resonance, we're going to use 3 curved arrows, using the new fishhook type of arrow. One fishhook arrow is going to take the unpaired electron down. Another one is going to take a single electron from the pi bond and bring it to the neighboring carbon-carbon bond. And a third curved arrow goes from the middle of the pi bond to the carbon on the left. The way these fishhook arrows are used, when you bring 2 fishhook arrows together, where they meet in the middle forms a new bond. So the 2 curved arrows where I take the radical down and a pi bond electron over is forming the new pi bond between these 2 carbons on the right. And in the fishhook arrow notation, you separate 2 electrons in order to break a bond using 2 fishhook arrows. So in the allylic example up above, I'm separating the 2 electrons from the pi bond, using one of those electrons to form a new pi bond, and one of those electrons is going to form the new radical. Before delving into particular reactions and their mechanisms, I want to talk about 6 common patterns that you'll see in radical reactions. The first pattern is known as homolytic cleavage. This is breaking a bond and creating 2 radicals, and this requires a lot of energy. You'll need energy in the form of light, written as hν, or heat, often written as a capital delta, in order to get this homolytic cleavage to occur. What this could look like is a sigma bond between 2 atoms being cleaved by treatment with light, hν, to create 2 radicals. So in the homolytic cleavage, the 2 electrons from the sigma bond get split evenly between the x's, creating 2 x radicals. The curved arrow pattern for a homolytic cleavage involves 2 curved arrows. They each have the tail of the curved arrow at the middle of the sigma bond, and the head of each curved arrow goes toward the x that's a part of the bond. Another common curved arrow pattern is known as addition to a pi bond. This involves a radical reacting with an alkene to generate a new radical. the addition to a pi bond mechanism is going to involve 3 fishhook arrows. I use 1 fishhook arrow from X going to a point in space, 1 fishhook arrow from the pi bond going to the same point in space, and a 3rd curved arrow from the pi bond going toward the end carbon of the alkene. These 2 fishhook arrows meeting together shows the formation of the new sigma bond between carbon and X, and the 3rd fishhook arrow shows the formation of the new carbon radical. Notice that in this addition to a pi bond type of pattern, a radical is adding to the pi bond, and you start out with 1 radical, and the product has a new radical that has been created. A 3rd common pattern for radical reactions is known as hydrogen abstraction. This involves a radical reacting with a bond to a hydrogen. In this example, R could be something like a carbon. In the products, a new bond between X and the hydrogen is formed, and a new R carbon radical is formed as a byproduct. Hydrogen abstraction is going to involve 3 curved arrows. 1 curved arrow from the X radical to a point in space, 1 curved arrow from the middle of the HR bond to the same point in space, and a 3rd curved arrow from the middle of the HR bond to R. So the 2 fishhook arrows that are meeting in the middle are showing the formation of the new XH bond, and the 3rd curved arrow shows the formation of the new radical. This is a new type of mechanism that we haven't seen before, that's transferring what's known as a hydrogen radical. Note that this is not the same as a proton transfer like we saw earlier for acid-base reactions. This is a neutral hydrogen, not a cationic one. The reaction known as a halogen abstraction involves the reaction of a radical with a halogen molecule. In the product, there's a new carbon-halogen bond, and a halogen radical has been created. Halogen abstraction is going to involve 3 fishhook arrows, 1 with the tail of the arrow at the radical going to a point in space, 1 at the sigma bond between the halogens to the same point in space, and 1 from the sigma bond going to one of the X atoms. The 2 fishhook arrows meeting at a single point in space show the formation of the new carbon-halogen bond, and the 3rd arrow going from the middle of the bond to a halogen shows the formation of a new radical. Halogen abstraction is similar to hydrogen abstraction that we saw previously. It's just a different type of radical and different type of bond that's breaking, but the curved arrow pattern is similar. A curved arrow pattern known as elimination involves the formation of a radical and an alkene from a molecule that has a radical at a position adjacent to one with a leaving group. This curved arrow pattern is going to involve 3 fishhook arrows, 1 bringing the radical down, 1 from the middle of the carbon X bond to the middle of the neighboring bond, and 1 from the carbon X bond going to X. The 2 fishhook arrows meeting in the middle of the carbon-carbon bond show the formation of a new pi bond, and the 3rd curved arrow going toward X forms the X radical. You can label the positions of the radical and the carbon adjacent to it as the alpha and the beta positions. The pi bond in the elimination reaction is forming between the alpha and beta positions, and the sigma bond between the beta carbon and the leaving group is the bond that's breaking in this step. And the 6th and final pattern for radical reactions is known as coupling. This involves 2 radicals coming together to form a new sigma bond. Coupling is going to involve 2 curved arrows. Each curved arrow has the tail at the radical, and the arrowhead at a point in space where the curved arrows are meeting. This shows those unpaired electrons coming together to form a new sigma bond. You can think about this coupling reaction as being the reverse of the homolytic cleavage reaction that we saw earlier. I want to show you some real molecule examples of what these curved arrow patterns could look like. I want you to start practicing identifying the curved arrow patterns as well as drawing them out. In this first example, there is a tertiary carbon radical reacting with HBr, and in the product, a new carbon-hydrogen bond has formed at that tertiary position, and a bromine radical has formed as well. Notice that the hydrogen is being transferred from bromine to carbon. So this is an example of a hydrogen abstraction reaction. This curved arrow pattern uses 3 fishhook arrows, one from the carbon radical to a point in space, one from the HBr bond to the same point in space, and one from that bond to bromine. These 3 arrows show the carbon-hydrogen bond forming and the new bromine radical forming. As another example, let's consider this alkyl peroxide starting material. It is being heated up to generate 2 oxygen radicals. Because a starting material containing no radicals was converted into 2 separate radicals, this is a homolytic cleavage event. This curved arrow pattern uses 2 curved arrows. Each curved arrow has its tail at the oxygen-oxygen bond and its fishhook head at one of the oxygens. As a third example, let's consider this carbon radical starting material that's reacting to form an alkene and a new radical. You could think about the products that formed as one is an alkene and the other radical must have served as a leaving group. You could identify the alpha and beta positions of the starting material, where the alpha is the one with the unpaired electron. And in this reaction, an elimination must have taken place. You draw radical eliminations with 3 curved arrows, bringing the radical down, and 1 electron over to form a pi bond, and 1 electron over to carbon to form the new radical. For the remainder of today's video, I'm going to be talking about the chlorination of methane reaction, which involves treatment of methane with Cl2 in the presence of light, Hnu, and the products of this reaction are chloromethane and HCl. Radical mechanisms are written a little bit different from ones we've seen before, and they're going to occur in 3 separate stages. The first stage of a radical reaction is known as initiation. This is the step that has a homolytic cleavage to create radicals. The second stage of a radical reaction is known as propagation. This is going to involve radicals reacting with molecules to create new radicals. And the final stage of a radical reaction is known as termination, and this is going to involve radicals coming together to form a sigma bond, essentially destroying the radicals. In general, initiation is going to involve breaking the weakest bond in the reaction mixture in order to create radicals. The carbon-hydrogen bonds of methane are very strong, and the chlorine-chlorine bond of Cl2 is significantly weaker. Therefore, it's this chlorine-chlorine sigma bond that's going to break in the initiation step. This homolytic cleavage is the one that's going to involve light, and that energy is needed to break that bond and create radicals. The initiation step in the homolytic cleavage will involve 2 curved arrows. This breaks the chlorine-chlorine bond to form 2 new chlorine radicals. In propagation steps, radicals are going to react to create new radicals. So you want to look for a radical on both the left and right sides of your propagation reaction steps. The chlorine radical is very reactive, and it can cause a hydrogen abstraction from the CH bond of methane. This hydrogen abstraction will involve 3 curved arrows, one from the chlorine radical, and one from the CH bond meeting together to form a new bond, and a third one from the CH bond to carbon. This hydrogen abstraction forms the new HCl bond, and it creates a methyl radical. Notice that the final product involving carbon is chloromethane, so we need to create a new carbon-chlorine bond in the next step of the mechanism. Rather than bringing in a chlorine radical, which is very low in concentration because radicals are so unstable, I'm going to use the methyl radical to react with another molecule of chlorine starting material. You can assume that not all of it cleaves by homolytic cleavage at the same time. The halogen abstraction will involve 3 curved arrows, one from the carbon radical, and one from the chlorine-chlorine bond meeting together, and a third one from the chlorine-chlorine bond to chlorine. This halogen abstraction step creates the new carbon-chlorine bond of the chloromethane product and generates a new chlorine radical. As I mentioned before, it's important that a propagation step has one radical starting out and one in the products, and notice that that's the case in each of the 2 propagation steps I drew. The termination phase of the mechanism is going to involve destroying radicals, or bringing them together to form bonds rather than radicals. Radicals are super reactive, and they can combine with each other if they encounter each other in solution, and there are going to be 3 different possibilities for termination events. One possibility is that 2 chlorine radicals could encounter each other in solution. These radicals could come together in a coupling reaction. This particular coupling would form a new chlorine-chlorine bond. Alternatively, it's possible that a chlorine radical could encounter a methyl radical in solution. So a second possibility is that a carbon radical and a chlorine radical couple together. This coupling reaction would form a new carbon-chlorine bond as a termination event. Or it's possible that 2 carbon radicals could encounter each other in solution, and these carbon radicals could come together, and this would form a new carbon-carbon bond as a termination event. So notice all 3 of the possibilities that I drew involved different radicals coming together to form a new sigma bond as a termination step. And notice the products of each of these steps involve no radicals. A really useful thing to look out for identifying the propagation steps of the mechanism is that the propagation steps will sum to give you the net reaction. So for the chlorination of methane reaction, I mentioned hydrogen abstraction and chlorine abstraction as the 2 propagation steps of the mechanism. This was involving a chlorine radical reacting with methane to make a methyl radical and HCl, and then a methyl radical reacting with Cl2 to make chloromethane and a chlorine radical. So we're going to imagine summing these 2 propagation steps together. Notice that a chlorine radical in the reactant side and the product side would cancel with each other when we sum these, and a methyl radical on either side would cancel as well. Summing the 2 propagation steps together gives the net reaction, which was methane reacting with chlorine to make chloromethane and HCl. Another thing to be on the lookout for is your propagation steps. If you use a radical in one, you should regenerate it in a later propagation step. So notice in the chlorination of methane, I used a chlorine radical in the first propagation step, and I remade it in the second propagation step. So notice in the second propagation step, I remade that chlorine radical, and it could go on to react with another equivalent of methane to cause the propagation step to keep going. There's a general term for this reaction in which a product of a later step acts as a reactant for an earlier step, and we would refer to this as a chain reaction mechanism. in this particular case, a radical chain mechanism. Another key thing to look out for in radical reactions was that initiation step. You can refer to the compound that has the weakest bond that breaks to form the radicals as the radical initiator. In the case of methane chlorination, Cl2 served as the initiator, and the chlorine-chlorine bond broke homolytically in order to form the radicals. This required light or heat. This step generated 2 new chlorine radicals, and a similar homolytic cleavage could occur for Br2 instead. It's also possible for other weak bonds to serve as initiators instead of Cl2. So for example, in the case of an alkyl peroxide, that bond between the 2 oxygens is fairly weak, and it can also be homolytically cleaved by either light or heat. That homolytic cleavage would have those 2 fishhook arrows, and it would form 2 oxygen radicals. And a special type of peroxide is known as an acyl peroxide, where each peroxide oxygen is attached to a carbonyl carbon. And this oxygen-oxygen bond is extremely weak. It can also be homolytically cleaved by treatment with light or heat. This homolytic cleavage would result in the formation of 2 oxygen radicals. And the reason that the oxygen-oxygen bond of the acyl peroxide is so weak is that the oxygen radical product is resonance stabilized in this case. So notice that the new oxygen radical is adjacent to a pi bond. So the radical is spread over 2 locations instead of 1, making it more stable, in the same way that anions and cations are also stabilized by resonance. Alright, so this video was our introduction to radicals and their reactions. I talked about how homolytic bond cleavage results in the formation of radicals. I talked about 6 common patterns for radical reactions that I want you to be able to identify the name of the pattern and also be able to draw its fishhook curved arrow mechanism for. And I ended with a specific example of a radical reaction known as the chlorination of methane. This involved 3 distinct stages known as initiation, propagation, and termination. That's it for this video. I will see you in class.